Hi, now this presentation is going to continue where we left off last time, where we have considered a good introduction of artificial neural networks. We've compared biological neurons, which we've found in the brain, based on the way they operate, how they fire, and we've seen a neuron is typically connected to many inputs. In this case, we have shown three, but there can be more. And each weight is have a corresponding weight attached to it here. And these weights actually determine what influence these inputs will have on the neuron. So this neuron now is going to accumulate all these inputs that are connected to it through their respective weights, and then compare to a given threshold to decide whether the output Y is going to represent firing, not firing, and so on. So we've looked at activation functions, which allow us to decide whether the neurons are firing or not, or actually to calculate the state output of a neuron given the inputs. So this is one operation we're doing on the inputs. We'll be taking the weighted sum. So we're taking every input multiplied by the respective weights with a capital X. So if you have here 10 weights, you're going to take a product of these 10 weights with the respective inputs, and then do accumulated sum of that. And then once you get to capital X, you're going to feed that capital X into an activation function to decide what level is your output. So we've looked at different activation functions. We've looked at a step, sine, sigmoid, and linear, and we have depicted them using graphs, so like more easier to follow. So it's a step activation function, and we mentioned last time that in this case here, your theta, your threshold is 0. But of course, when we start training neural network, the data would be primed to be also adjusting. So this graph here can shift left or right. The step sign is simply between 1 and -1. So these two activation functions, as we'll be seeing in a few minutes, are actually hard limiter functions. So they allow us to do classification. So this part here would be, let's say, one class, and this one is second class. So this one can be 1 or 0, or the classes can be represented as 1 and -1. We'll be starting the perceptron, which does only a classification between two classes, but it is of course possible to extend to more than two classes. We look at a sigmoid activation function, which will become handy when we start to talk about multi-layer perceptron. We'll see why we cannot use hard limiter functions with multi-layer perceptron, and when do we need to use multi-layer perceptrons. This is one of the main aim of today's session. And the linear one, like we said last time, is not a hard limiter function. It's the continuous function here, y is equal to x. It's not capped anywhere. If you look at this one, the sigmoid function, when capital X tends to infinity, it is capped at 1 and -1, but it is not the case for the linear function. It's not bounded by any limits. And we have seen typical the linear function is for linear approximation, which you can look at examples. So based on the content you're recovering, you can easily use an activation function, a linear, to replicate a relationship between y and x based on linear approximation. So we've already covered these things in the part 1 video. Now, next we want to look at the perceptron. The perceptron, like we said, is the simplest form of neural network because it consists of only one neuron. It consists of one neuron with adjustable synaptic weights. So these weights here, W1, W2, are adjustable. In this case, we're showing a perceptron with 2 inputs only, but the number of inputs can be much more. But a perceptron is just one neuron. That is the important definition of a perceptron is one neuron, but the number of inputs can be more, and you have only one output, because we have said every neuron has only one output, and we have also talked about the bias, the threshold theta, which is used to decide when the neuron actually fires or not. So is this theta is fundamental in defining the state of output y. Now the activation function, which will be used for the perceptron, is a hard limiter, so it can be either step or sign, because the perceptron actually is used to classify, to separate between different classes. So it could be this class or that class. So we can clearly see here your output is not continuous. It's either one class or the other. Yep. So this diagram we just seen in the previous slide. Now, if you extend that a bit further to show the function that's happening inside this neuron here, then we come to this diagram here, where, like you see it initially, once you get your inputs x, and in this case x1, x2, but it could be more, you will multiply x1 by its weight, x2 by its weight, and then you're going to do a summation. So you will do this summation to get the weighted sum to get capital X. So this is what we're showing here. We're dividing the neuron into two parts. So one part is to do the accumulation, the summation of the product of weights with the respective weights. And then once you get that, then you're going to feed that capital X to an activation function. In this case, since the hard limit function, we're showing it here as a step. Yep. Do a very sharp transition here. We could, of course, also separate these two functions like is shown here now. So we take, in this case, we're showing three inputs. So x1, w1, x2, w2, x3, w3. So what we're going to do now, first, you're going to do a summation. You're going to take x1 times w1 plus x2 times w2 plus x3 times w3 to get to capital X. Then this capital X is fed an activation function, which would, of course, have as input the threshold as well. And based on these different signals, you can calculate Y. Now, one observation like we've done when we were discussing the operation of neural networks, firing and not firing. So your W1 here is going to be some value, and this was going to decide your capital X. Is X1 increasing capital X, or is it decreasing capital X? Or if W1 was simply 0, means this input X1 is not having an influence on the cumulated sum, the weighted sum you're calculating. Okay, so in a way, this W1, W2, W3 is where intelligence is stored in your network. So this is what we actually adjust as we're learning. So the intelligence in a neural network is stored in these various weights, because these weights are fundamental in deciding what output do we get. Is it firing or not, and in interest as well. Yep. So like we said, we're going to calculate the weighted sum of inputs first and supply the hard limiter function, which produces an output equal to +1 if this input is positive and -1 if it is negative. So here you're using a sign activation function, as you can see here. And we do compare the threshold theta. Yeah. So if when you compare it, your capital X is more than or equal to theta, then you produce an output +1. If your capital X is less than theta, then you're producing -1. The aim of a perceptron in this case is to classify inputs into one of two classes. It is possible to extend this to design a perceptron which is classifying between more than two classes. But let's start with this one with two classes. Now let's come to this equation that you're finding here. So this actually xi multiplied by wi is your capital X. So what you first calculate your capital X, and if you have n inputs, you're going to compute this weighted sum over all your inputs and the respective weights. This is what I is starting at 1 and going to n. Once you've done that, then we are subtracting theta here. This is simply saying here we are comparing the value of capital X to theta. And you can clearly see, what did we say? If capital X is more than or equal to theta, you get one class. If it is less than theta, you get a second class. So clearly, this is a decision boundary. This is a separation between these two classes. So in case your n was 2, means you have x1, x2, then this is the equation you're getting, because your capital X will be x1 w1 plus x2 w2 minus theta. It's equal to 0. So this is clearly an equation of a straight line. If you imagine x1 to be, let's say, y, and x2 to be x, and you get an equation for y is equal to mx plus c. So this becomes your decision boundary, it's a straight line. If n was equal to 3, then you get the equation x1 w1 plus x2 w2 plus x3 w3 minus theta is equal to 0. This is the equation of a plane now. So what we're trying to stress out here is, if the number of dimensions you have in your feature space for your input was 2, then we can sketch that and show that the decision boundary between the two classes is actually a straight line. This is the equation of that line. If you had 3 dimensions in your feature space, your input feature space, then you're getting x1 w1 plus x2 w2 plus x3 w3 minus theta equals to 0. That's the equation of a plane. Yep. So this plane actually is not just this triangle here; it extends infinity in a way. And above this plane is one class, and below that plane is second class. Now, if your the number of dimensions in your feature space exceeds 3, then you're not able to depict that. It's not easy to depict things in 4D. So you're limited by 3 dimensions in Cartesian space. But if you had, let's say, 4 dimensions, you'd have x1 w1 plus x2 w2 plus x3 w3 plus x4 w4 minus theta equals to 0. What we're stressing out here is problems which can be solved by the perceptron have to be linearly separated, irrespective of the number of dimensions you have. Here we can show it 2 dimensions is line, 3 dimensions is a plane, but if you go to high dimensions, even if you have 10 dimensions or 20 or 100 dimensions, for you to use a perceptron, the decision boundary has to be linearly separable. We'll come back to this in greater detail as we go along. So let's see the operation of the perceptron by using a very simple training set. So we're going to use logical operations here, because logical operations like AND, OR, XOR, or AND, NAND, NOR, and so on, they are well defined. But of course, this is a very simplistic but a very powerful way to illustrate the operation of a perceptron. But in practice, you could be collecting data for x1, x2, which doesn't need to be binary, but the output typically be either yes or no, true or false of this form, because here you're classifying your output in one of 2 classes, or if you are more than 2 classes, then you can extend a perceptron to do that. Okay, so let's consider these 3 logical operations, AND, OR, and XOR. So that's straightforward here. AND is simply you're ending these 2, and the AND operation would have a high when both of your inputs are high. The OR operation would have a high when at least one of your inputs is true or high. And XOR is very similar to OR, except that the condition when both are high is not taken as a condition for high, so it's exclusive. So the inputs have to be exclusively different. Exclusive means you don't take the condition 1, 1, or 1 here. So if you want to use to train the perceptron to actually replicate the AND, OR, and XOR, because your output is binary, you could use a perceptron for that. And in this case, we are using 2 input AND or operations, so your perceptron have 2 inputs. So let's try to represent these logical operations on 2D plots, very similar to what we've done here. So in this case here, we're going to have a class 1. When your output for your AND is 1, that's the 1 class, and when it's low, it's another class. This is what you're trying to show. And your x1 and x2 would simply be these 2 inputs here. So if you try to depict the AND operation on a 2D plot, so you have x1 and x2. So we have these 3 conditions here. There's 3 conditions here: 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, and 1, 0, where your output are actually all zeros. That's what we have shown here on this plot as an unshaded circle for the classes which are for the outputs which are low, and then for the 1 instance where your output is actually high, when you have 1, 1, then you get the 1. This is what we've shown here as a shaded circle. So in this case here, if you want to separate these 2 classes, so again, what are your 2 classes here? So false state or 0 state would be 1 class, and this 1 state here, the true state, would be another class. You can easily draw a straight line between the 2. It means this problem is linearly separate. Yeah. So one approach which we do, a very simplistic one here, if you draw the equation of this line, if you draw a line here and find the equation of this line, for example, if you find it, you can represent it of this form: 0.1 x1 plus 0.1 x2 minus 0.2 equals to 0. Then this will be the equation of this line. Why we're doing it of this form? Because remember, it was x1 w1. So if you were to set w1 to 0.1, w2 to 0.1, and your threshold is always subtracted from this weighted sum. So if you set your data at 0.2, then you get a line like this. That's down the neural network. So this neural network, this perceptron here, is able to represent your AND logical expression. Okay. Now, before we go to the OR, maybe I would want to describe a bit more in detail why this particular combination of W1, W2, and theta are actually representing your logical AND operation. This may not be clear at this point. Let's just take an example here in the table. Let's take 0, 0, we should be getting 0. So if this one was a 0 here, so we take 0 times 0.1 plus 0 times 0.1, so you weighted some capital X to 0, we subtract 0.2, so we get minus 0.2 as your capital X minus theta. So if you take a step of that, step or sign of that, so step of minus 0.2 is 0. So this is where you get the 0 here. So if you were to take x1 as 0 and x2 as 0, so you take x1 here as 0 and x2 as 1, so you get 0 times 0.1, you get 0, and then you take 1 times 0.1, you get 0.1, so 0 plus 0.1, you get 0.1 for capital X minus 0.2, 0.1 minus 0.2, you get minus 0.1, in step of minus 0.1, you're getting a 0. So same thing for this one. So the only point where you're actually getting a high for your n was when x1 and x2 were both 0 or both 1. So if you take 1 times 0.1 plus 1 times 0.1, 0.1 plus 0.1, you're going to get 0.2 minus 0.2. So you get capital X minus theta of 0. And remember when you're considering steps, so a step of 0 is actually 1. That's exactly the threshold. So this particular combination of weights and your 0.2 actually produce the in a perceptron, a trained network to replicate the end operation. Now let's look at the O. So the O, we've said in this case we have 3 instances which are of class 1 and only 1 instance which is class 0. This is when x1 and x2 are both 0. And then when you have all the other 3 combinations, so when x1 is 0 and x1 is 1 and x1 is 1 and x2 is 0 here, you get a 1. When x1 is 0 and x2 is 1, you also get a 1 for your output, so true. When both are high, of course, you are again getting a 1 to class 1. So this 3 instances of class 1, and this one in the instance of class 0 can be separated by this line here. So it means the perceptron can actually replicate this particular data set. And just like we've done before, if you can draw a line here, it's not a unique line. You could be shifting this line between this threshold here. You could be changing the gradients as long as it's separating the 2 classes. For this particular case here, if you were to set your W1 at 0.1, W2 again at 0.1, but you set your threshold at only 0.1, you are able to separate. So let's again do the same procedure we've just done earlier for the N. So this particular instance here, when x1 and x2 are both 0, you expect to get an output of 0. So if we were to replace this one by 0 here and a 0, so you get 0 minus 0.1, take step or minus 0.1, you get 0. That's fine. Now these 3 combinations here should produce an output high, an output of true. So let's see here, in this case, this one is x1 is 1, x2 is 0. So if you take 0.1 plus 0, is 0.1 times 1, so 0.1 plus 0.1 times 0, so you get 0. So 0.1 minus 0.1, you get 0. So step of 0 is high, so you get the high here. Same thing for this one, you will also get a high. And this one, when both are 1, so you're getting a 1 here, a 1 here, you get 0.1 plus 0.1, 0.2 minus 0.1, you get 0.1, step of 0.1 is high. You can clearly see here by putting the weights at 0.1 and the bias threshold at 0.1 again, you're able to replicate the O operation. Okay, now the method we have used here is quite simplistic because we have a very limited data set with only 4 instances of the 4 combinations of x1, x2, and that's representing all the possible combinations. If you have 2 inputs of a binary variable, we have only 4 combinations. So here we are able to represent all 4 of them. But in practice, you might have much more than 4 combinations, especially if your x1, x2 are not binary. They can be any number, any value. If the number of dimensions you have x1 or 2, like here, you can very easily just do a scatter plot and then see if you can put a straight line in there. And if you can find the equation of this line, you're done. You can very easily set the weights, but it's not always easy to do that. So later in another video, we're going to see how can we train Perceptron to actually not set W1, W2, and theta in this way by drawing a line, but by just setting random values initially and allowing the algorithm to convert the values, allow you to separate 2 classes. This will be the subject of the next video, which we're going to look at how to train your neural networks, start with Perceptron, and the last video will be on multi-layer Perceptron. Now let's move on to the logical XOR. So XOR, like we said, is very similar to OR, except that in the last case here, when X1 and X2 are both 1, you actually have a low value. So if we shift to XOR operation, this is what we get. So you have two values here. You have two values here which are high. Actually, the XOR operation is likened to be the difference gate. So whenever your X1 and X2 are different, you have a high class, and when the two inputs have the same state, so in this case 0 0, your output is 0, 1 1 is also 0. So it's likened to be the difference gate. You would have come across an XNOR gate now, where these two would be low and these two are high, and then we call this XNOR gate the parity gate. So let's come back to the XOR function. So the question is, can a perceptron be used to represent this operation? So basically you're asking, can a perceptron be used to replicate the XOR operation? The answer is very simple. Can you draw, because here we are having two inputs, X1, X2, can we draw a single line, not a piecewise line, but a single line which can separate two classes? In these two cases was very straightforward. You can just draw a straight line here, it separated two classes. For XOR, for operation as well, we've seen you can draw a straight line here to separate your class 1 and your class 0. But here, if you put it, for example, if you put a straight line here, you're not separating the two classes, because you have a class 0 here, you have a class 0 underneath as well. So if you try to imagine all possibilities of a straight line to separate these two classes, it's impossible to do that. You might have to come across something like this, maybe. Yep, like this here. Is it? Everything above the addition boundary would be class 1. Everything below the addition boundary would be class below the addition boundary would be class 0. So you can clearly see here we can't draw a straight line to do that. Means the perceptron cannot be used to replicate the XOR function. So later in the next video, when we'll start understanding presenting the tools and the algorithms we'll be using to do the training for the perceptron, we can try to apply this algorithm on the XOR function, and you'll see that it will actually not converge. You will not be able to train it. Okay, so like we said, perceptron is able to represent a function only if there is some line or plane that separates the two classes. That is, if they are linearly separable. We've said line for 2D, a plane for 3D, but when you come to 4D, it's difficult to see what type of geometry is that, what type of addition boundary you're getting, but definitely it's a product of X1 and W1, and then you're simply comparing to your threshold theta. So this becomes a linearly separable problem. So clearly the XOR function was not linearly separable. So this is why we are clearly saying we cannot use the perceptron to represent it. So irrespective of the activation function employed, a single layer perceptron can classify only linearly separable patterns. Yep. So the inability of the perceptron to represent linearly separable problems is not because you're using hard limit functions, simply because you're accumulating and comparing to a threshold. Okay. So to deal with non-linearly separable problems, so if you come across, for example, the problem as XOR function, and you try to train a neural network not converging, most likely your problem is non-linearly separable, and then you'll have to go for an MLP, a multi-layer perceptron. If I just go one slide forward, this is how a multi-layer perceptron will look like. You don't have only one neurons now. If you understood what a perceptron is, a multi-layer perceptron would have many of its perceptrons. So in a multi-layer perceptron, you will always have an input layer. This is where your inputs are coming into the system. These neurons which you have here are non-processing neurons. They don't have an activation function as part of the operation. They're just taking this inputs and just feeding it the next layer. So these neurons here would actually do the summation and the activation we've talked about. Okay, and multi-layer perceptron, like you're seeing this diagram is fully connected. So if you take, for example, this neuron here is fully connected to all the other neurons in the previous layer, as well as in the next state. So this is what an MLP is about. You have as architecture of neural network was not necessarily the case, but we're considering MLP as a very good start for you to learn about different types of neural networks. You can, of course, go on your own and read other types of neural networks you're not fully connected or using different approaches, but it's a very good start. Now, this is called input layer. You definitely need to have an output layer. So if you are considering, for example, XOR function, you want to develop an MLP for it. So you have two inputs and then you would have one neuron only with one output because you have only one output. Now, what sits between the input and the output would be a hidden layer. Okay? So hidden layer is going to take these inputs, process it, and then feed its output as an input output layer. And of course, these neurons you find here in the output layer would be having a summation and activation. Now, why we call this layer here a hidden layer? Because the states you have inside this layer here are not known to the real world. So this is a real world, this is a real world. What is sitting in between here is inside the processor, inside your system. So this part is called hidden layer. For this reason, the states that you have here are hidden to the external world. So we'll be, of course, seeing how you train a multi-layer perceptron after having learned the method to train a perceptron. And it's based on the same method, but we'll be having some complications, which we'll explain later. So if we come one slide back here, we see a multi-layer perceptron, the feed-forward neural network with one or more hidden layers. So in this diagram here, we are showing only one hidden layer, but for some problems, you might need to consider more than one hidden layer. And in one hidden layer, the number of neurons you're choosing here can also be varied to be able to replicate a given problem. So these are parameters you will be playing around when you're trying to train a neural network for a given process. We've discussed that typically the network consists of an input layer of source neurons. So these we said are non-computational neurons. At least one middle or hidden layer of computational neurons. Computational neurons we're saying here, they are having the summation and activation, and an output of computational neurons again. So the output neurons are also having summation and activation. Okay, so I'm going to step here and just a quick recap of what we've covered here. Fundamental for us was to understand activation. So based on the inputs you have to a given perceptron or a neuron in general, you're going to do the summation. You find the weighted sum of inputs, which you will then compare the threshold theta, and then you feed that to an activation function. And we've looked at the perceptron here as the simplest neural network that can be used to solve linearly separable problems. And we've seen one method you could do that to assess whether you can actually separate your classes would be to do a scatter plot, and then if you can draw a straight line between your two classes or more classes which you have, then a perceptron can be used. And if you can't do that, like we've seen the case of the XOR function, then you would have to consider more complex neural network. The MLP is one solution, but you might have others you can consider, and we're going to look at that now in the next video I'm going to send. It will be about training of perceptron based on, so this was the first neural network which could be trained quite far back, and it has been used very effectively with time, but the training of MLP was a bit more complicated. It took quite a lot of time from the time we could train a perceptron and then train an MLP. It took quite a bit of time to resolve the complexity there. So we're going to discuss all this in the next video, and thank you for your attention.